Collaborators are Tiber Cassius. He is a Ph.D. candidate in the Department of Construction, Civil, and Environmental Engineering. And his co-mentor is Jose Serrato Corrales with the Center for Water and the Environment. And I'm with the center, I'm the director for the Center for Microengineered Materials. So this represents a nice collaboration between two UNM centers. So in a nutshell, UNM has developed a novel in-situ monitor for detecting heavy metals in water streams. Now the applications for this most of the applications are pretty obvious. We all want to have water quality which meets or exceeds EPA standards. And many of us are aware of the health problems when you have mercury, arsenic, chromium, cadmium, for example, toxic heavy metals within the water. And the sources vary tremendously from geologic sources to anthropogenic sources, such as discharge from plants. And many industrial applications, such as plating baths, for example, use electrodeposition, use some of these metals, and there are strict discharge regulations related to what your discharge water streams can have in terms of these metal concentrations. So there's a need for analysis of water streams. Continuous analysis is always nicer than batch-based analysis. Current techniques for the batch-based analysis are primarily spectrographic or chromographic methods, which require a skilled operator. And while there's a lot of automation, there's a lot of robotics involved these days, it still requires quite a bit of oversight, and the cost of the instrumentation is expensive. There's a lot of consumables involved, and you need somebody who really knows what they're doing to watch over the equipment. So some of the techniques which we use include flow-through analysis by electrochemical pre-concentration, detection and quantification. We use an innovative pH-controlled polymer electrolyte membrane technique to eliminate the need for replacement electrolyte solutions every time you perform an analysis. There is a need in electrochemical electroanalysis techniques to have a reference potential. We generate this continuously in situ by water electrolysis. There is also the need in many cases to replace consumables such as electrode materials and electrolytes, as I mentioned before. And our design greatly decreases the number of consumable materials by using in situ regeneration of the working materials. And as I mentioned before, this technique is capable of detecting iron, lead, copper, mercury, arsenic, chromium, cadmium, and some other ions which may or may not be of interest depending on the process. So let me see if I can there we go. So a very brief background in the technique which I'm using. The technique which I'm using is electroanalysis. Voltammetric techniques are some of the oldest instrumental chemical analysis techniques around. However, there's new innovations which are being developed, particularly in the materials which are used, and the cost of the electronics has decreased exponentially over the last few years. So in voltammetry, what we're using essentially is an electrochemical method which provides information about concentrations of an analyte by looking at a current which involves electron exchange between the analyte and the electrodes. And it's a function of applied potential. And the potential gives us some information about what species we are detecting. So the instrumentation consists typically of 2 or 3 electrodes in solution containing the analyte. We have a working electrode. This is the electrode where the potential is varied with time. We have a reference electrode, which remains constant. So we have something to reference our working electrode potential against, the standard reference potential. We have a counter electrode, which acts as the current collection source for our experiment. We have an electrolyte, which is used to conduct the ion current within our system. So anodic stripping voltammetry is a subset of voltammetric and electroanalysis methods. And it's one of the most sensitive electroanalysis techniques because it actually pre-concentrates the species which you're trying to detect. So this is typically done in an electrochemical cell, which is illustrated up here, where there's a working electrode, there's a reference electrode, a counter electrode, the ability to introduce gases into the cell or other solutions within the cell, and stirring of the cell. In anodic stripping voltammetry, what you want to do, is first to, from a known concentration of fluid, you want to deposit whatever you're trying to analyze, the metal you're trying to analyze, by reducing the ions in solution to metals which stick to the working electrode surface. This is done by applying a potential where the ion will spontaneously be reduced to the metal and be captured onto the electrode. And you can vary this time in order to change the sensitivity of the technique and the potential to target the specific species. These species reduce at different potentials. But we're not using this primarily as the detection technique. We're using this as a concentration technique. What you do is that you then change the potential, you sweep the potential so that the analyte is redissolved or stripped. It's oxidized, it's converted back into ions, and you measure that current. And that current is proportional to the concentration, and the potential can be used to identify the species. And so what I have here in the diagram is at first the excitation potential, which strips the ions out of solution, and a sweep of voltage from a negative voltage to the reference voltage, which shows the stripping of the metal being oxidized off of the analysis electrode back into solution, showing the detection of cadmium here and the detection of copper. And if you integrate the area underneath these peaks, this gives you the ability to quantify the amount of material which was deposited on the electrodes. So this can get below parts per million concentrations down to parts per billion concentrations within the analytical range, which is required for EPA level analyses. Here's an illustration of a laboratory setup here. This is courtesy of Metrorome. They develop a lot of the benchtop and field analytical equipment, which uses analytical stripping technology. And again, it's a batch technique. And these are some of the ions and the potential ranges which they're stripped over. So you can see zinc, cadmium, lead, nickel, copper, mercury, arsenic, chromium, gold, which is rarely in your solution, or selenium, which are less likely. So what we have done is we have developed a number of different components for building a system which continuously can analyze for heavy metals by stripping voltammetry. And here's an example of the flow cell in real dimensions. This is about 3 inches by 3 inches square. This is just showing it hooked up on our laboratory benchtop. And what we have here on the left-hand side is the results of the stripping of arsenic, which was pre-concentrated onto an electrode as a function of concentration. And so we have a blank, we have 5 micrograms per liter, which is below the EPA limit. 10 micrograms per liter is the EPA drinking water limit. And then we have higher concentrations, 15, 25, 50. And the integrated area under the peak follows a very nice calibration curve here. We've tested our electrode materials on waters, natural waters within the state of New Mexico with common interfering ions and ions which might be an interference, common ions in the water such as sodium, chloride, sulfate, potassium, and we still get a nice linear correlation here. Here's an example for iron, where in each one of these cycles there's successive additions of iron into the solution which is flowing through, and you see the increasing peak height indicative of the higher concentrations as it's continuously flowed through the cells. You know, there's a number of things which make this cell novel compared to some of the past techniques, besides being able to be used continuously. So in this cell, what we have is we've developed a very low-cost gold-coated carbon working electrode. And by gold coating, we're literally talking about a layer of less than 10 nanometers of gold on the carbon surface. So the loading is micrograms of gold. So it's insignificant, the amount of gold here, as opposed to systems which use gold wires and gold foils, which are or printed gold thick film layers, which cost hundreds of dollars for a single electrode. And you do have to replace electrodes sometimes in these techniques, so that lowers the cost of that significantly. And so using RF sputter deposition techniques, we have been able to greatly decrease the gold loading used in these techniques by orders of magnitude compared to other commercially available technologies. So we have our thick film electrode here. What we do is we flow our solution through here, and we have a special membrane here, which is a proton conducting membrane, which gives us constant pH. And this polymer membrane substitutes for the electrolyte solution. And so it does not, and it can be regenerated, and it can be regenerated by a counter electrode here, which can take the water, split the water, and regenerate protons for the replacement of, if any of the protons here get consumed in the reaction, it can regenerate the membrane. So you are at constant pH, which is a requirement for these. You have an electrolyte, which is a requirement for here, but it's a solid state polymer membrane. And we use platinum nanoparticles deposited on carbon as our electrode, which can act as both the reference electrode and the counter electrode, where we split where water is split on the regeneration cycle. And we can supply, it does need a reference gas here. The reference gas can be supplied from a second smaller electrolysis cell, which is built on similar technology, which just takes water and generates a very low rate supply of hydrogen to keep the potential on this electrode during the stripping experiment constant, so that we have a good reference here. So we have a very simple cell configuration with a setup which generates its own reagent for the reference electrode, which is hydrogen. It gives the ability to regenerate the membrane if the membrane starts to get fouled with other ions. And it gives us the ability then to perform stripping voltammetry on our ultra low loading gold thin films. So as I mentioned before, the application of course here is for continuous water quality monitoring. Again, we're down to micrograms of gold used for the analyzer electrode. And it's the same quantities really on the platinum electrode. The platinum electrode probably does not need to be replaced in the lifetime of the instrument. This enables multiple species identification. This is easy to interface to the cloud, to the Internet of Things. And on a different project, we're working with a company at developing actually electronics for sensors, not this sensor, but for other sensors, but it's quite applicable in a very small package which can perform the data reduction and the communications to the internet. This can give a dramatic reduction in waste generation, unlike the batch techniques where you're constantly building up, you constantly need to be replacing electrolyte solutions and refilling reagents. It's much lower cost than ion chromatography, atomic absorption spectroscopy, inductive coupled plasma, optical emission spectroscopy, or induction coupled plasma mass spectroscopy. And so obvious uses besides water treatment plants and industrial discharge monitoring, it may be effective for on-site well drilling water quality assessment. Wouldn't it be nice that if a well is being drilled and you have different, in the state of New Mexico, for example, you have many perched aquifers and the water chemistry is substantially different. Typically today, what we do is we select for the water based on how quickly the aquifer can supply water, not on the water quality, because there's no way in real time to be able to, while the drilling is occurring, to assess what the water quality is from these separate aquifers which you drill into. And so this gives the ability to say, well, this is a go or no go aquifer. It's way too, the water has way too high of a heavy metals content. Let's go drill someplace else, or let's go deeper, for example. Those are good examples for this. And of course, if you're performing environmental investigations, there are many places where, unfortunately, we have chromium contamination. You can use this technique possibly in conjunction with drilling and water sampling in order to assess the water quality. So that's a short version. Alex, how far behind are we today?
Yeah, let me, I think we are somewhat behind. I think if you have a little bit more that you want to share, then that's fine. If not, we're about 8 minutes behind, so.
Okay, I'll go ahead and take questions.